Tonight we're going to talk about the closest star beyond our Sun, Alpha Centauri. You've probably heard that it is our nearest stellar neighbour, just over 4 light-years away, and that sounds close, at least in cosmic terms, the next star over, the house beside ours in the galaxy. But here's what changes everything. When you stop treating 4 light-years like a small number and start understanding what that distance actually means, the picture becomes almost unsettling. Because Alpha Centauri is not simply far away. It represents a barrier so enormous that even our fastest machines would need thousands of years to cross it. That reveals something humbling. We are far more isolated than we imagine, and by the end of tonight, you're going to understand exactly why the distance to Alpha Centauri represents one of the toughest challenges humanity has ever faced. If you enjoy this type of content, consider liking and subscribing to the channel. It truly helps me. Now get comfortable. Let's begin. Alpha Centauri is often spoken about as if it were one star, a single bright point sitting beside our Sun in the enormous darkness of space. But that simple idea is already misleading. Alpha Centauri is not one star. It is a system, a small family of stars bound together by gravity, moving through the galaxy as one connected structure. From Earth, it looks like a point of light. Through a telescope, it becomes something more complex. And when we study it carefully, we find that our nearest stellar neighbour is not a lonely sun at all, but a place with motion, history, architecture, and scale. The 2 main stars are called Alpha Centauri A and Alpha Centauri B. They orbit each other in a slow gravitational dance, circling a shared centre of mass once every 79 to 80 years. That means one full orbit takes about as long as a human lifetime. A child born when the 2 stars are in one position might be an old person by the time they return to that same arrangement again. Their orbit is not a perfect circle either. It is stretched like an oval path carved into the dark. Sometimes the 2 stars come relatively close together. At other times they swing far apart, widening the space between them. At their closest, Alpha Centauri A and B are separated by about the distance between the Sun and Saturn. At their farthest, they are farther apart than the Sun and Neptune. So even inside this nearby star system, the distances are already enormous. If you could somehow stand on a planet orbiting one of these stars, the other would not simply look like an ordinary star in the sky. It would shine far brighter than any star we see from Earth. It might cast shadows at night. It might feel like a second sun, distant but powerful, turning the sky into something both familiar and alien. Alpha Centauri A is the larger and brighter of the pair. In many ways, it is remarkably similar to our Sun. It is slightly more massive, somewhat more luminous, and made of the same basic ingredients: hydrogen, helium, and heavier elements forged in earlier generations of stars. If our Sun were replaced by Alpha Centauri A, Earth would not instantly become unrecognizable. The planet would receive more light and heat, but the star itself would feel familiar. It is not a monster star, not a blue giant burning itself out in a cosmic flash, not a dying red giant swallowing its planets. It is a stable, middle-aged star, fusing hydrogen in its core, shining steadily across billions of years. Alpha Centauri B is smaller and dimmer, but still deeply familiar in a cosmic sense. It is also a main sequence star, which means it is in the long, stable stage of stellar life, where hydrogen is converted into helium in its core. It is less massive than the Sun, and gives off less light, so a planet would need to orbit closer to receive the same warmth Earth receives from our Sun. But it is still the kind of star that can last for billions of years, the kind of star around which planets could, in principle, have long histories. If Alpha Centauri A is like a slightly grander version of the Sun, Alpha Centauri B is like a quieter, smaller sibling. Together, these 2 stars form the bright heart of the Alpha Centauri system. They have been circling each other for longer than human imagination can comfortably hold. Their motion has continued through the entire rise of civilization on Earth. They were orbiting each other before the first cities, before writing, before agriculture, before the first humans looked up and gave names to the stars. They were orbiting each other when Earth was covered by ancient forests, when dinosaurs walked under different skies, and when the continents themselves were arranged differently. Stars move on clocks that make human history seem like the turning of a single page. But the system has a third member, and this is the one that matters most to our story. Far beyond Alpha Centauri A and B lies Proxima Centauri. The name Proxima means nearest, and that is exactly what it is. Proxima Centauri is the closest known star to the Sun. It is not bright like Alpha Centauri A. It is not sun-like in the way Alpha Centauri B is. Proxima is a red dwarf, a small, cool, faint star with only a fraction of the Sun's mass and a tiny fraction of its brightness. If you placed Proxima where the Sun is, Earth would freeze. The star is simply too dim to warm our planet from that distance. Red dwarfs like Proxima are easy to underestimate because they are faint. Most cannot be seen with the naked eye, even when they are relatively close. But they are the most common stars in the galaxy. The Milky Way is not mostly filled with stars like the Sun. It is filled with small red stars burning quietly in the dark, conserving their fuel, shining with patience on timescales far longer than stars like ours. Proxima Centauri may seem modest, but stars like it are the long-term survivors of the universe. Our Sun will eventually swell, die, and fade into a white dwarf. Proxima may continue shining for trillions of years. Proxima sits far from the central pair, so far that its relationship with Alpha Centauri A and B was not obvious at first. It orbits them at an immense distance, roughly 13,000 astronomical units away. An astronomical unit is the distance from Earth to the Sun, so this is not a small separation. It is not like 3 stars crowded together in a tight room. It is more like 2 bright lanterns in the centre of a vast estate, with a small red ember circling far out near the boundary. Proxima is gravitationally connected, but distant enough that it feels almost like a separate outpost. Its orbit around Alpha Centauri A and B may take hundreds of thousands of years. Think about that for a moment. In the time Proxima completes a single loop around the central stars, entire species can rise and vanish on Earth. Ice ages can come and go. Human beings can evolve, spread across the planet, invent language, build civilizations, and send machines into space. Proxima's path is so large that the story of humanity so far occupies only a tiny fraction of one orbit. This is what stellar architecture looks like when measured honestly. Even the nearest star system contains distances that dwarf our familiar sense of space and time. And yet, despite all that vastness inside the system itself, Alpha Centauri is still the nearest one. Beyond our Sun, there is nothing closer. Not Sirius, not Barnard's star, not the bright stars that dominate the night sky. Alpha Centauri is the next step outward. It is the first shore beyond the solar system. That is what makes it so important. When people imagine interstellar travel, this is the natural first destination. Not because it is easy, but because everything else is worse. If we cannot reach Alpha Centauri, then every other star is even farther away, every other dream even more difficult. The strange thing is that Alpha Centauri feels familiar and unreachable at the same time. Its stars are not exotic monsters. They are not mysterious objects at the edge of the observable universe. 2 of them resemble our Sun. One of them has at least one planet that has drawn enormous scientific attention. The system is close enough that its light arrives in just over 4 years. Close enough for astronomers to study in detail. Close enough to become a symbol of possible exploration. And yet, that closeness is deceptive. 4 light years sounds almost gentle until you turn it into a journey. This is the first lesson Alpha Centauri teaches us. The universe uses the word near differently than we do. On Earth, near means across the street, across town, across a border, maybe across an ocean. In the solar system, near already becomes strange. The Moon is near, but still hundreds of thousands of miles away. Mars is near, but still months away by spacecraft. Pluto is near in the sense that it belongs to our solar system, but a mission to Pluto took almost a decade. Then comes Alpha Centauri, the nearest star system, and suddenly the scale breaks open completely. It is the house next door in the galaxy, but the road to that house is 25 trillion miles long. It is our closest stellar neighbour, but its light has already been travelling for years by the time it reaches our eyes. It is familiar enough to tempt us, but distant enough to humble us. Alpha Centauri does not just introduce us to another star system, it introduces us to the real scale of interstellar space, and once that scale becomes clear, the next question becomes unavoidable. What does 4.24 light years actually mean? Not as a number, but as a barrier. The number itself sounds almost harmless. 4.24 light years. It is short enough to fit neatly into a sentence, short enough to seem almost manageable. 4 years is not a mythic span of time. A person can finish school in 4 years. A city can build towers in 4 years. A child can go from crawling to asking questions about the Moon. So when we hear that the closest star is just over 4 light years away, the mind does something natural. It shrinks the distance. It turns Alpha Centauri into a neighbour, the next house over, the next island across the water, close, at least by the standards of the galaxy. But that phrase hides the real scale of the problem. A light year is not a year. It is the distance light travels in a year, and light moves at about 186,000 miles every second. That is the fastest speed anything in the universe can travel. It is not a record waiting to be broken. It is not an engineering challenge we have not solved yet. It is a boundary written into physics. In 1 second, light can circle Earth more than 7 times. In just over 1 second, it can cross the distance from the Moon to Earth. In about 8 minutes, sunlight travels from the surface of the Sun to your face. That is already fast beyond instinct. But even that speed needs more than 4 years to reach Alpha Centauri. After 1 year, light has travelled almost 6 trillion miles. That is what 1 light year really means. Now multiply it by more than 4. Proxima Centauri sits about 25 trillion miles away, and Alpha Centauri A and B are slightly farther still. To make that number feel real, imagine every mile as a single page in a book. The distance to the Moon would make a stack taller than a skyscraper. The distance to the Sun would become a library. But the distance to Alpha Centauri would be a mountain range of books stretching beyond the horizon. You could spend your entire life turning pages and still never reach the final chapter. That is the hidden violence of interstellar distance. It takes a clean, simple number and turns it into something almost impossible to carry in the mind. The solar system already feels enormous, but compared with the space between stars, it is only a small clearing. The Moon is about 1¼ light seconds away. The Sun is about 8 light minutes away. Mars, depending on where it is in its orbit, can be several light minutes away. Jupiter is tens of light minutes away. Pluto is several light hours away. These distances are difficult, but they still belong to the Sun's domain. They are rooms inside the same house. Alpha Centauri is not another room. It is not even another building on the same street. It is a separate fire burning across a wilderness so wide that our entire planetary system becomes almost local by comparison. This is one of the most important truths about space. The planets are far apart, but the stars are separated by emptiness on another level entirely. Between Earth and Mars there are challenges: fuel, timing, radiation, landing. survival. Between the Sun and Alpha Centauri, there is a different kind of challenge. There is almost nothing. No stations, no planets, no emergency harbour, no place to stop and repair. Just darkness, stray atoms, dust grains, radiation, and distance. It is not like crossing an ocean with islands along the way. It is like crossing an ocean where the nearest shore is so far away that generations could live and die before the coastline appears. That distance changes the meaning of communication. A radio signal to the moon can go there and come back in a few seconds. A message to Mars may take minutes each way, which is inconvenient but still workable. Engineers can send commands, wait for confirmation, and adjust the mission. A spacecraft near Pluto is hours away by radio, and even that delay is something mission teams can manage. But a signal to Alpha Centauri would take 4.24 years just to arrive. A reply would take another 4.24 years to return. The fastest possible exchange with the nearest star system would take about 8.5 years. That is not conversation in any ordinary human sense. It is more like writing a letter to the future. Ask a question today, and the answer returns in another chapter of your life. A child could send a message and receive the reply as a teenager. A young scientist could begin a project and hear the response after their life has already changed direction. Even if there were someone at Alpha Centauri listening, we could not speak with them the way two people speak across a table. We could only exchange delayed fragments, separated not by bad technology, but by the structure of the universe itself. And this delay is not only about messages, it also shapes what we see. When you look at Alpha Centauri, you are looking into the past. The light entering your eye or telescope left that system more than 4 years ago. You're not seeing Alpha Centauri as it is right now. You're seeing it as it was when that light began its journey. For a stable star, 4 years is almost nothing. Alpha Centauri will not change dramatically in that time, but the principle is enormous. The sky is not a live image, it is an archive. Every star is a message from an earlier moment. The farther away the star, the older the message. If something dramatic happened on Proxima Centauri today, Earth would not know. There would be no instant warning, no cosmic alert, no sudden update in the sky. The old light would keep arriving, calm and unchanged, carrying news from before the event. Only years later would the truth reach us. This is one of the strangest parts of astronomy. The universe does not show itself all at once. It arrives in layers of time. The nearest star beyond the Sun is already 4 years behind the present. The bright stars across the galaxy may be hundreds or thousands of years behind. Distant galaxies show us light that began travelling before humans existed. Looking outward is also looking backward. For most of history, humanity did not know how deep the sky really was. The stars looked fixed, distant, and mysterious, but no one could measure their true separation from Earth. They were lights in the heavens, points on a celestial ceiling. Some philosophers imagined they might be other suns, but imagination is not measurement. The breakthrough came through parallax, one of the most elegant ideas in astronomy. Hold up a finger in front of your face and close one eye, then the other. Your finger appears to shift against the background. The finger has not moved. Your viewpoint has. Astronomers used Earth's orbit in the same way. They observed a star from one side of the Sun, then months later from the other side, and looked for a tiny shift against the more distant stars behind it. For Alpha Centauri, that shift is incredibly small, less than 1 arcsecond. An arcsecond is such a tiny angle that it barely belongs to human vision at all. It is like trying to notice the apparent movement of a coin from miles away. Yet in the 19th century, astronomers measured it. With careful instruments, repeated observations, and enormous patience, they detected the tiny wobble that revealed Alpha Centauri's distance. And when the calculation was made, the result was stunning. The closest stars were not simply far away. They were separated from us by gulfs so enormous that the solar system itself became small. That discovery changed humanity's mental map of the universe. Before stellar distances were measured, the night sky could still feel like a dome above Earth. Afterward, it became an ocean with no visible shore. The stars were not nearby lamps. They were suns scattered across unimaginable emptiness. Alpha Centauri became the first milestone beyond our solar system, the nearest address in interstellar space. But the first milestone was already almost unreachable. This is why 4.24 light-years is such a deceptive number. It sounds precise, clean, and scientific. But inside it is a distance that turns our fastest spacecraft into drifting dust. Inside it is a communication delay longer than many relationships. Inside it is the realization that the nearest star is not waiting just outside our door. It is across a silence so large that even light, the fastest thing in existence, needs years to cross it. And this is only the beginning of the problem. Understanding the distance as light travels it is one thing. But light is not a spacecraft. Light does not carry fuel. It does not need shielding. It does not worry about dust grains, radiation, broken electronics, or human bodies sealed inside a fragile machine. Light does not need to slow down when it arrives. It simply moves at the limit nature allows. So the next question is much harsher. If even light needs more than 4 years to cross the gap, how long would it take us? Now the distance stops being an idea and becomes a journey. It is one thing to say Alpha Centauri is 4.24 light-years away. It is another thing to ask what kind of machine could actually cross that space. This is where the numbers become less like astronomy and more like a warning. The universe does not care how close a star looks on a map. It only cares about distance, speed, energy, and time. The fastest spacecraft humans have ever built are astonishing by ordinary standards. The Parker Solar Probe, diving close to the Sun and using the Sun's gravity to accelerate, can reach speeds of hundreds of thousands of miles per hour. On Earth, that is almost unimaginable. At that speed, a spacecraft could cross oceans in moments, circle the planet faster than a person could finish a meal, and reach the Moon in less than an hour. But point that speed toward Alpha Centauri and it becomes painfully slow. A spacecraft travelling at Parker Solar Probe speeds would still need thousands of years to reach the nearest star. Longer than the entire span of recorded civilization. If such a spacecraft had launched when the earliest known empires were rising, it would still be travelling today, still not there, still moving through the dark with much of the journey ahead. That is the first brutal lesson of interstellar travel. Human speed and cosmic distance do not belong to the same scale. Voyager 1, one of the most famous spacecraft ever launched, is already in interstellar space. It has crossed the boundary where the solar wind gives way to the material between stars. It carries a golden record, a message from our planet, a small archive of human sounds, images, and hopes. And yet, compared with the distance to Alpha Centauri, Voyager has barely left the doorstep. It is not aimed at Alpha Centauri, but even if it were, the journey would take tens of thousands of years. Tens of thousands of years ago, human beings were hunter-gatherers. There were no cities, no writing, no nations, no science, no telescopes, no engines, no maps of the stars. Almost everything we recognize as civilization has happened in less time than Voyager would need to reach the nearest star. A probe travelling at that speed would not be a mission in the normal sense. It would be an artifact cast into deep time, and this is before we ask whether the spacecraft would still work when it arrived. Machines do not remain healthy forever. Electronics degrade, power sources weaken, materials are damaged by radiation. Tiny impacts leave scars. A spacecraft that survives a decade is already an engineering triumph. At current speeds, Alpha Centauri asks for something far beyond that. A machine that can survive for thousands or tens of thousands of years with no repair, no refueling, no rescue, and no second chance. So the obvious answer is speed. To reach another star in any meaningful time, a spacecraft must travel much faster than anything we have built. Not twice as fast, not 10 times as fast, hundreds or thousands of times faster. We have to stop thinking in miles per hour and start thinking in fractions of light speed. 1% of light speed sounds small, almost modest, but it is about 6.7 million miles per hour, far beyond our current spacecraft. At 1% of light speed, the journey to Alpha Centauri would still take more than 400 years, shorter than tens of thousands, but still longer than any human life. A mission at that speed would have to be a multi-century project, launched by one civilization and received by another. The people who designed it would never see it arrive. Their children would not see it arrive. Their grandchildren might not see it arrive. A crewed mission at that speed becomes even stranger. It would need to be a generation ship, a moving world designed to keep human beings alive for centuries. The first passengers would depart Earth knowing they would never arrive. Their children would be born inside the ship, live inside the ship, and likely die inside the ship. Their grandchildren would inherit a destination chosen before they existed. The mission would become less like travel and more like ancestry. This raises questions that are not just technical. Is it fair to place unborn generations inside a journey they did not choose? On Earth, people can leave a city, cross a border, change their future. On a generation ship, there is nowhere else to go. The ship is the country, the landscape, the weather, the horizon, and the prison. Every corridor becomes part of the world. Every system failure becomes a natural disaster. Now imagine increasing the speed to 10% of light speed. This begins to feel more reasonable at first. At that speed, Alpha Centauri could be reached in about 42 years. Long, but possible within a single human lifetime. Someone could leave Earth young and arrive old. The journey would no longer require centuries of inherited purpose. It would become a life's work, a voyage longer than most careers, but not longer than a human story. But 10% of light speed brings its own violence. At that speed, space itself becomes dangerous. The emptiness between stars contains gas and dust. Not much, but enough. A grain of sand hitting a spacecraft at 10% of light speed would release devastating energy. A tiny particle becomes a bullet. A slightly larger particle becomes a bomb. The spacecraft would need shielding strong enough to survive impacts from things too small to see, moving with energies no ordinary armor was designed to absorb. And every kilogram of shielding makes the spacecraft heavier, which means it takes more energy to accelerate. To go faster, you need more energy. To protect the ship, you need more mass. More mass requires even more energy. If you carry fuel, you must also accelerate the fuel. Then you need fuel to accelerate that fuel. The math becomes merciless. This is the rocket equation, one of the great walls between humanity and the stars. That is why serious interstellar concepts reach for strange technologies. Fusion drives, using the same basic energy source that powers stars. Nuclear pulse propulsion, where a spacecraft rides the force of repeated nuclear explosions. Antimatter engines, where matter and antimatter destroy each other and release enormous energy. Laser sails, where a powerful beam from Earth or orbit pushes an ultralight spacecraft to extreme speed without the craft carrying its own fuel. Each idea is rooted in real physics. The problem is building them. Fusion propulsion would require systems far beyond what we can place on a spacecraft today. Antimatter propulsion would require antimatter in quantities we cannot produce practically. Nuclear pulse propulsion is physically plausible, but politically difficult. Laser sails require immense laser arrays, astonishing precision, and materials that can survive being pushed by beams powerful enough to destroy them if they absorb even a tiny fraction of the energy. Even if one of these systems worked, the destination creates another problem: slowing down. Reaching Alpha Centauri is not enough. A flyby mission could race through the system, take measurements, and vanish into the dark beyond. But to enter orbit, study planets carefully, or land, the spacecraft must lose the speed it spent so much energy gaining. Deceleration can be just as hard as acceleration. Many proposed interstellar probes avoid this by accepting a flyby. They would spend decades crossing space, then have only hours or days near the target. Imagine crossing an ocean for half your life and seeing the new continent only from a window as you fly past it at impossible speed. That may still be scientifically valuable. A few close images of another star system would be historic. But it is not the same as arrival. It is not settlement. It is not standing on a new shore. It is a glance, earned at enormous cost. And this is only for the nearest star. Alpha Centauri is the easy case. Every other destination is worse. If the nearest star already demands impossible speeds, radical propulsion, heavy shielding, multi-decade missions and communication delays measured in years, then the galaxy is not an open plain waiting for us to walk across it. It is a continent of islands separated by oceans so wide that even the closest crossing may define the limits of human ambition. That is what makes Alpha Centauri so humbling. It is close enough to tempt us, close enough to name, study, imagine, and plan for. But once we turn it from a point of light into a destination, it becomes a wall. Our engines are too slow, our fuel is too heavy, our machines are too fragile, our lives are too short. The stars are not forbidden by myth. They are separated from us by ordinary physics carried to an extraordinary scale, and so the next star becomes a test, not just of engineering, but of patience, energy, survival, and meaning. We can see it, we can measure it, we can describe it with beautiful precision, but seeing is not reaching. Knowing is not crossing. The space between us and Alpha Centauri is filled with every problem that appears when a small species tries to move beyond the world that made it. The journey to Alpha Centauri is often imagined as a straight line through emptiness. A spacecraft leaves the solar system, points toward the nearest star, and moves through a silent black ocean until the destination grows brighter ahead. But the space between stars is not truly empty. It is emptier than anything we can create in a laboratory, but it is not nothing. It contains atoms, dust grains, magnetic fields, radiation, and ancient particles moving at nearly the speed of light. For a slow spacecraft, this may seem almost irrelevant. For a spacecraft moving at a fraction of light speed, it becomes a landscape of invisible hazards. The material between stars is called the interstellar medium. The name sounds gentle, almost like a thin mist, but it is not mist in any familiar sense. On Earth, the air around you contains an unimaginable number of molecules in every breath. Even the best vacuum chambers we build still contain more matter than deep space. Between stars there may be only a few atoms in a cubic centimetre, sometimes less. By earthly standards, that is almost perfect emptiness. But over 25 trillion miles, even almost nothing adds up. A spacecraft crossing that distance does not pass through a small patch of vacuum. It cuts through an enormous volume of space, collecting risk one atom and one dust grain at a time. At ordinary speeds, a hydrogen atom is harmless. A dust particle is harmless. They're too small, too light, too insignificant to worry about, but speed changes the meaning of impact. At 10 or 20% of light speed, the spacecraft is not simply moving through space. It is turning space into a particle beam. Every atom ahead becomes something the ship must collide with or deflect. Every dust grain becomes a possible catastrophe. The danger is not because interstellar space is crowded. It is dangerous because the ship is moving so fast that even tiny things strike with enormous energy. This is one of the strangest truths about going fast. The faster you move, the more violent the universe becomes. A grain of dust that would drift unnoticed past a normal spacecraft can hit like an explosive at interstellar velocity. A particle too small to see can puncture, vaporize, or damage delicate instruments. A slightly larger grain could destroy a small probe completely. The front of an interstellar craft would need to behave like the bow of an icebreaker, except the ice is invisible, scattered across light years, and each collision happens at speeds no ship on Earth has ever faced. Shielding sounds like the simple answer, but shielding is never simple in space. A thicker shield means more protection, but it also means more mass. More mass means more energy to accelerate. More energy means more fuel, larger engines, or a more powerful launch system. The shield that protects the spacecraft also makes the spacecraft harder to send. This is why interstellar design becomes a chain of trade-offs. Add protection, and the mission becomes heavier. Make the ship lighter, and it becomes more fragile. Increase speed, and the trip becomes shorter, but the impacts become more destructive. Slow down, and the danger from impacts drops, but the journey stretches across lifetimes or centuries. Radiation is another enemy, quieter but just as serious. Space is filled with cosmic rays, high-energy particles launched by violent events such as supernovae and other extreme astrophysical processes. These particles pass through space from all directions. On Earth, the atmosphere and magnetic field protect us. They form a kind of planetary roof, absorbing or deflecting much of the radiation before it reaches the ground. Even astronauts near Earth still receive higher doses than people on the surface, but they remain partly sheltered by Earth's magnetic environment. An interstellar spacecraft would leave that protection behind. Beyond the solar system, there is no planetary magnetic field wrapped around the crew, no atmosphere, no nearby world to hide behind. A crewed ship would spend years or decades exposed to radiation that can damage electronics and living tissue. In the human body, high-energy particles can break DNA, increase cancer risk, and harm organs over time. In computers, radiation can corrupt memory, damage circuits, and slowly weaken the systems that keep the mission alive. A spacecraft travelling to Alpha Centauri would not simply need to survive launch and acceleration. It would need to remain healthy through decades of invisible bombardment. Water could help. So could thick layers of material rich in hydrogen. Some designs imagine surrounding the crew compartment with water tanks, using the same water needed for life support as radiation shielding. This is elegant because one resource serves two purposes, but water is heavy. Every litre must be accelerated along with the ship. Magnetic shielding is another possibility, creating an artificial field around the spacecraft, something like a miniature version of Earth's magnetosphere. But magnetic shields require power, equipment, cooling, and reliability over enormous timescales. They may deflect charged particles, but not everything is charged. Some radiation still demands physical shielding. Then there is the problem of repair. On Earth, machines survive because they are maintained, bridges are inspected, aircraft are serviced, power plants have replacement parts, even spacecraft near Earth are supported by teams who can send instructions, adjust software, and work around failures. But an interstellar spacecraft would be alone. If a sensor fails halfway to Alpha Centauri, there is no warehouse of parts nearby. If a shield is damaged by dust, no repair crew can be launched from Earth to meet it. If a critical system begins to degrade, the ship must diagnose and fix itself, or the crew must do it with whatever tools and materials they brought. This means an interstellar craft cannot be only a vehicle. It must be a workshop, a factory, a hospital, and a habitat. It must carry spare parts, raw materials, repair systems, and people or machines capable of using them. The more self-sufficient it becomes, the heavier it becomes. The heavier it is, the harder it is to accelerate. Once again, the same trap appears. Survival demands mass, but speed punishes mass. The ship must be strong enough to endure the journey and light enough to begin it. Navigation is also more difficult than it seems. Alpha Centauri is not sitting still, waiting like a lighthouse fixed on a shore. It is moving through the galaxy, and so are we. The Sun orbits the centre of the Milky Way. Alpha Centauri follows its own path. Over years or decades, the target shifts. A spacecraft cannot simply aim at where Alpha Centauri appears in the sky today. It must aim at where the system will be when the spacecraft arrives. The mission must lead the target, like throwing a ball not to where someone is standing, but to where they will be when the ball reaches them. Over interstellar distances, tiny errors become enormous. A small mistake in direction near Earth can grow into millions or billions of miles at the destination. A fraction of a degree may be the difference between passing close enough to study a planet and missing the system entirely. Course correction is possible only if the spacecraft has fuel, guidance, instruments, and time. But every correction uses resources. Every resource adds mass. A mission to Alpha Centauri would need precision on a scale far beyond ordinary travel. It is not like sailing toward a continent. It is like trying to thread a needle from another continent while both the needle and the archer are moving. And when the spacecraft finally approaches the system, the problem becomes even sharper. Alpha Centauri is not a single target. It contains two sun-like stars and the distant red dwarf Proxima. Proxima is the closest and has a known planet of special interest, but it is far from Alpha Centauri A and B. A fast flyby probe cannot casually visit all three. It must choose a path before arrival. Aim for Proxima and its planet, or aim for the brighter central pair. The system that looked like one point from Earth becomes, up close, a vast region with separate destinations divided by enormous distances. This is why the empty space between us and Alpha Centauri is not just a waiting room, it is part of the challenge. It tests the spacecraft before the star system ever comes into view. It grinds down materials, exposes electronics, threatens biology, magnifies navigation errors, and forces every design choice into conflict with every other design choice. The journey is not only about building a faster engine, it is about surviving the road when the road is nearly invisible and more than 4 light-years long. Science fiction often skips this part because it is slow, technical, and unforgiving. A starship jumps, warps, or slides through hyperspace, and the empty distance becomes a transition between scenes. But in the real universe, the distance is the story. The darkness between stars is not a blank page. It is the main chapter. It is where the mission spends almost all of its time, where most failures would happen, where the dream of reaching another sun would either survive or quietly end. And that is what makes Alpha Centauri feel even more distant. The difficulty is not only that it lies 25 trillion miles away. The difficulty is that every mile must be crossed under the rules of physics. Every mile exposes the spacecraft to risk. Every mile increases the need for systems that can endure without help. The nearest star is not guarded by a wall we can see. It is guarded by emptiness itself, and emptiness, stretched across light years, may be one of the most formidable barriers in the universe. Even if a spacecraft survived the journey, another problem would follow it the entire way. Silence. Not complete silence, because radio messages could still travel between Earth and the ship, but silence in the human sense. No live conversation, no immediate advice, no quick correction from mission control. The farther the spacecraft moves from Earth, the more time begins to stretch between question and answer. Distance does not only separate places, it separates people into different moments. At first, the delay would feel strange but manageable. If a ship were still inside the outer solar system, messages might take hours to arrive. That is already difficult, but space missions today can work with delays like that. Engineers can plan, crews can wait, instructions can be sent, received and followed. But once the ship is truly on its way to Alpha Centauri, the delay begins to grow into something more than inconvenience. After months or years of travel, Earth is no longer a control center in any ordinary sense. It becomes a distant source of old information. At 1/10 of the speed of light, after 1 year of travel, the ship would be about 1/10 of a light year from Earth. A message from home would take more than a month to arrive. A reply would take more than a month to return. That means even early in the mission, a simple exchange could last many weeks. Ask for advice about a technical problem, and the answer may arrive after the situation has already changed. Send a report about a system failure, and by the time Earth receives it, the crew may have fixed it, adapted to it, or suffered the consequences. After 10 years, the ship would be about 1 light year from Earth. Now messages take a year each way. Earth hears what happened long after it happened. The crew receives news that is already a year old. A war could begin and end before the ship learns how it started. A government could change. A scientific discovery could transform the mission's assumptions. People on Earth could celebrate, panic, mourn, and rebuild, while the crew only receives the echoes later, like listening to history instead of news. After 20 years, the delay becomes even more isolating. The ship is now deep in interstellar space, farther from Earth than any human has ever imagined living. Radio signals weaken with distance. They spread out, becoming thinner and harder to detect. To keep communication alive, both Earth and the spacecraft would need powerful transmitters, large antennas, careful aiming, and enormous patience. Every message would have to be treated as precious. There would be no casual calls, no constant stream of conversation, no feeling of being connected to the world in real time. Earth would become less like a home speaking from behind you, and more like a lighthouse whose beam takes years to sweep across the sea. This changes the psychology of the mission. Human beings are not only machines that require oxygen, food, and temperature control. We are social creatures. We orient ourselves through response. A question answered quickly tells us we're not alone. A face on a screen, a voice in the room, even a message that arrives within seconds can hold a person inside a shared world. But on the way to Alpha Centauri, response slows until the shared world begins to tear. The crew may still love Earth, remember Earth, and serve a mission designed on Earth, but they would no longer live in Earth's present. That separation would become especially powerful for a crewed mission lasting decades. The people on board would develop their own routines, their own language of survival, their own private history. Small events that matter deeply to them might mean very little to Earth years later. A damaged valve, a medical emergency, an argument over resources, a birth, a death, a repair that saves the ship. All of it would unfold in real time only for the people inside the vessel. Earth would hear about it afterward. Earth would respond afterward. Earth would care, perhaps deeply, but always too late to participate. For a generation ship, the separation becomes even more profound. The first passengers would leave with memories of oceans, forests, weather, cities, and open skies. Their children might know those things only through recordings. Their grandchildren might know Earth as an origin story, the way people today know ancient homelands through books, songs, and inherited names. The planet that built the ship would slowly transform from a real place into a symbol. Blue oceans, white clouds, continents under sunlight. Beautiful, sacred, but unreachable. Earth would become less a location and more a myth with photographs. This is one of the most unsettling possibilities of interstellar travel. To settle another star system would not simply expand humanity, it might divide humanity. A colony around Alpha Centauri would not be like a city across an ocean or a research station in Antarctica. Those places are remote, but they are still connected to Earth's shared present. People can travel to them and return, Messages move instantly or nearly instantly. Supplies can be sent. Decisions can be coordinated. A colony 4 light-years away would be different. It would be connected by memory, biology, and light-speed messages, but not by daily life. Over generations, that gap would widen. Language would change. Customs would change. Laws would change. Problems would be different because the environment would be different. A society living under another star, perhaps inside habitats, perhaps on a planet around Proxima, would make choices Earth could not fully understand. Earth would do the same. Each civilization would grow under different pressures. After a few centuries, they might still share a common ancestry, but their cultures could feel foreign to each other. Not alien, exactly, but no longer the same. This is not necessarily tragic. It may be how expansion across the stars would have to work. On Earth, separated human groups have always changed over time, adapting to geography, climate, resources, and history. The difference is that Earth eventually reconnects its separated peoples. Oceans can be crossed, languages can be translated, trade routes can form, migration can renew contact. Between stars, reconnection is far harder. The ocean is too wide, the crossing too slow, and the letters take years. Interstellar civilization may not become one great galactic society. It may become an archipelago of isolated human islands, each visible to the others only by delayed light. And then there is the question of arrival. Science fiction often treats arrival as the end of the journey, the moment the music rises and the new sun fills the window. But reaching Alpha Centauri would not solve the problem of distance. It would make the distance permanent. Once a crew or colony arrives, Earth is not suddenly close again. It is still 4.24 light-years away. A message saying, "We made it," would take more than 4 years to reach home. Earth's congratulations would take another 4 years to return. By the time the crew hears the reply, they would have been living with the consequences of arrival for nearly a decade. If the mission is a fast flyby, the emotional strangeness becomes even sharper. A probe might spend 20 or 40 years crossing interstellar space, only to pass through the Alpha Centauri system in hours or days. It would take its photographs, measure what it could, and then vanish into deeper space. The data would travel back to Earth for more than 4 years. Scientists would open the message long after the probe had already left the system forever. The most important discoveries might come from a machine that is no longer anywhere near the world it studied. If the mission carries humans and can slow down, the questions become heavier. Where do they go first? Proxima Centauri has a known planet that may be scientifically fascinating, but Proxima is a small, active red dwarf. Alpha Centauri A and B are more sun-like, but any planets around them remain harder to study from Earth. The system is not a single destination. It is a vast arrangement of possible targets. Choosing one path may mean giving up another. Even arrival demands sacrifice. And if settlers remain there, they become something new. Not a replacement for Earth. Not an extension of Earth in the ordinary sense. A separate branch. A human community under different skies, governed by different necessities, shaped by a delay too large for real-time control. Earth could not manage such a colony minute by minute, or even year by year. It would have to let go. The colony would have to govern itself, repair itself, feed itself, and define itself. Independence would not be a political choice at first. It would be a physical fact. This is the hidden cost of the distance to the next star. The problem is not only crossing it. The problem is what crossing does to the connection behind you. A bridge that takes years for even light to cross is not a normal bridge. It is a thread stretched across time. It can carry messages, memories, discoveries, and grief, but it cannot carry immediacy. It cannot carry shared days. It cannot keep two worlds inside the same present. So Alpha Centauri is not just a destination, it is a threshold. On this side is the solar system, where Earth remains the centre of human experience, even when spacecraft travel far from home. On the other side is something different, a future where distance may separate not only planets and stars, but cultures, histories, and identities. To go there would be one of the greatest achievements imaginable. But it would also mean accepting that the universe does not give us expansion for free. Every new shore comes with an ocean behind it, and this ocean is measured in years of light. And this is only the nearest star. That is the part that makes the distance feel heavier the longer you think about it. Alpha Centauri is not a remote destination chosen because it is dramatic or exotic. It is not some faraway jewel on the other side of the galaxy. It is the closest one, the first step, the easiest target nature gives us beyond the Sun. If the galaxy were a map, Alpha Centauri would be the first dot outside our home territory. And even that first dot is almost beyond reach. Everything after it becomes worse. Barnard's star is farther. Sirius is farther still. Many of the bright stars that shape our constellations are tens, hundreds, or even thousands of light years away. They look close because the night sky flattens distance into a pattern. From Earth, the stars seem painted on the same dark ceiling, as if they all belong to one surface, but they do not. One star may be a few light years away. Another, beside it in the same constellation, may be hundreds of light years farther. The sky is not a ceiling, it is a depth, a cathedral with no back wall. This is why the Milky Way is so difficult to comprehend. It contains hundreds of billions of stars and probably even more planets. From a distance, a galaxy looks like a glowing island, a soft spiral of light. But inside that spiral, the stars are separated by enormous gulfs. A galaxy is not crowded in the way a city is crowded. It is more like a continent of lighthouses, each one shining across an ocean, each one visible, but separated by waters so wide that crossing from one to the next may require more than a civilization can easily give. Alpha Centauri teaches us that the galaxy is not open space waiting to be travelled. It is structured by distance. The emptiness between stars is not a minor detail. It is the main architecture. We tend to imagine the stars as destinations like ports on a map, but the map leaves out the scale of the ocean. It shows the dots and not the years. It shows the names and not the cost. The nearest harbour is already so far away that even reaching it would demand new physics-level engineering, generations of commitment, and a willingness to accept isolation as part of the journey. This does not mean interstellar travel is impossible. Physics does not forbid a spacecraft from reaching Alpha Centauri. The distance is not a magical wall. A machine could cross it, in principle, if it had enough speed, enough energy, enough protection, and enough time. Tiny probes pushed by lasers may someday make the attempt. Future engines may reduce the journey from millennia to decades. New materials, smarter navigation, and better power systems may open doors that seem closed today. Human history is full of achievements that once looked absurd. But there is a difference between impossible and practical. The universe often lives in that difference. It may be possible to send something to another star, but extremely difficult to send something useful. It may be possible to send a probe, but far harder to slow it down. It may be possible to send machines, but far harder to send people. It may be possible to create a colony, but far harder to keep it connected to Earth in any meaningful sense. Each step adds weight. Each ambition demands more energy, more time, more risk, and more acceptance of loss. This is where science fiction can quietly mislead us. Stories often make the galaxy feel navigable. A ship jumps to another system. A civilization spreads across stars. Planets become settings, and distance becomes background. That vision is beautiful, and it has inspired generations of scientists, engineers, and dreamers. But the real universe is more stubborn. There is no known shortcut around the speed of light, no confirmed warp drive, no hyperspace corridor, no hidden road through the dark. The stars are visible, but visibility is not accessibility. And that truth changes how we think about the future. For a long time, many people have imagined space as an escape hatch. If Earth becomes damaged, we will go somewhere else. If resources run low, we will expand outward. If civilization fails here, perhaps it can begin again under another sun. There is hope in that idea, but also danger, because the next star is not a backup plan waiting nearby. Alpha Centauri is 25 trillion miles away. Any world there, even if one proved habitable, would not be a place we could easily move to. It would not be a lifeboat for billions of people. It would not save us from problems we refuse to solve at home. Earth, by contrast, is here. It is not light years away. It is under our feet, around our lungs, inside our blood. Its oceans regulate the climate. Its atmosphere shields us from radiation. Its magnetic field helps protect the surface from charged particles. Its soil grows food. Its biosphere recycles air, water, and nutrients with a complexity no machine has ever matched. Every forest, river, cloud, insect, microbe, and ocean current is part of a life support system so advanced that we often forget we're inside it. When Alpha Centauri reveals how isolated we are, it also reveals how precious Earth is. Not because exploration is wrong, and not because the stars should be ignored. We should keep looking outward. We should build better telescopes, study exoplanets, search for life, test new propulsion, and send probes as far as our technology allows. Curiosity is one of the finest things about humanity. But curiosity should not become denial. The stars are not close enough to excuse neglect. The dream of distant worlds should make this world more valuable, not less. There is also a kind of beauty in the difficulty. If Alpha Centauri were easy to reach, perhaps we would take it for granted. Because it is hard, it forces us to understand the scale of the cosmos honestly. It reminds us that the universe was not built around human convenience. It does not shrink itself to fit our lifetimes. It does not soften its distances because we are curious. The stars shine whether we can reach them or not. They are not cruel, they are simply vast. And maybe that is the most important lesson. The distance to the next star does not make humanity meaningless. It makes our moment more astonishing. On one small planet, around one ordinary star, matter became aware of the sky. Atoms learned to ask where the other lights are. A species that once feared the night now measures the distance to suns it may never touch. That is not failure. That is extraordinary. Even if we never stand beneath the light of Alpha Centauri, knowing what it is and how far away it lies is already a form of crossing. Still, the distance remains. 4.24 light-years, a clean number hiding a 25 trillion mile gulf, the closest star beyond the Sun, the nearest neighbour, the first step into the galaxy, and it is so far away that our fastest machines would need thousands of years, our boldest concepts would need decades, and our messages would need years just to arrive. So when we look up at the night sky, the stars should not feel smaller, because they are unreachable. They should feel larger, more real, more humbling. They are not decorative lights above us. They are distant suns across an ocean of time. Alpha Centauri is the closest shore beyond our solar system, and even that shore may remain out of reach for generations. For now, we live on the island that made us. We look outward from Earth, sending light, machines, mathematics, and imagination into the dark. The next star is there, bright and real, waiting in the southern sky. But between us and that light is a distance worse than most people think, not because it destroys wonder, but because it deepens it. The universe is larger than our dreams, and that may be the most beautiful and humbling truth of all. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.